So today we are going to do a review of the electron configuration, valence electrons, and how to write down the Lewis-Dot structure, then hybridization, VSEPR, resonance, meaning of the formal charges. So all these things we are going to do in one complete way, like in one flow. So there are questions based on the molecules, their structures, hybridization, valence electrons, sigma bonds, pi bonds. So today we are trying to understand how to give answers very fast. So you are already aware of electron configurations. So let's start with electron configuration. Give me 1 second. Okay, can you hear me now? Okay, starting again. So let's write down the configuration of Br. So you already know that you know the configuration, how to write down the configuration. Before we start writing for Br, let's write down for this last element. Last element. Okay, starting from period number 1. In period number 1, there is 1s. Period number 1 is 1s. Period number 2, what is this one? 2s. Then this one, 2p. This one, period number 3, 3s, 3p. This, 4s, 4s. And what is this, children? This one? Yes, Isabella? Yes, it is 3d. Then this one is 4s, 3d, 4p. Now tell me about period number 5. Period number 5 is 5s. Then after 5s, what is this one? 4d. Then 5p. Period number 6, 6s. Then after 6s, what is this? This one. This one, this one. 4f, yes, 6s, 4f, and this one is 5d, and then 6p. Now, can you answer for the seventh period? Like this is period number 1, this is period number 2, this is period number 3, period number 4, period number 5, period number 6. Now, period number 7. Yes, tell me about period number 7. Start from here. Yes, who is this? Aditi, very good. 7s, 5f, and then 6d and 7p. So this is the configuration up to last element. Now, how many electrons you can have in s orbital? S can have how many electrons? 2. P can have 6. D can have D, Afan, 10. Very good. F can have 14. Perfect. Okay, now what's the meaning of valence electrons? Valence electrons. The electrons, yes, the electrons present in the outermost shell. Outermost shell means the one with the highest number of n, and the shell number. So, outermost shell. And then understand this word. Outermost shell, or the one with highest n value. Highest n. And you remember shell number. N is a shell number, n value. So take care of this definition of valence electrons, and now we are ready to write down some electron configuration. Ready? Give the electron configuration of bromine. And you are going to give me in terms of noble gas notation. So it is argon, this element, and this is period number 4. Yes. Yes, bromine. What is this? 4s2, 3d10, and 4p5. Now tell me what is the outermost valence shell? Outermost valence shell. Remember I gave you the definition. Outermost valence shell is the full one. Yes, the fourth one, Kiki. Very good. 4s2, 4p5. This one. So how many valence electrons are there? 7. Check. It is in which family? Halogen family. This is also called as 7th family. If I just ignore this particular numbering, and if I do the numbering like this, 1, 2, I can take it as 3, 4, 5, 6, 7. So there are 7 valence electrons, halogen family. 7th family, and this is 8th family. 7th family has 7 valence electrons. Give me the electron configuration of calcium. In terms of noble gas notation, all of you please write it. Those who are not able to write, please ask questions here. Okay, we are doing for calcium. Calcium is argon 4s2. So how many valence electrons are there? So valence electrons, and what is the group number? Group number and valence electrons are same. For S and P block, this is S block, children. You're aware of the S block? This is S block, this is P block. For S and P block, as only S and P block, S and P, valence electrons are equal to the group number. If I just block the D block, D and F, valence electrons is the group number. So you have to just look at the element, and if it is here, how many valence electrons? Arsenic? How many? 5, yes. Can we write down the configuration of aluminum? Aluminum. So all of you, please give me the electron configuration of aluminum. It is neon 3s2. Yes, Kiki, good. Neon 3s2, 3p1. So how many valence electrons? How many valence electrons? 3. And it is in the third group. So this is one important thing for practice. Second important, when ions are made, ions, the one with the negative and positive charge. Like for example, if I say sulfur, if I say what's the electron configuration of sulfur? So in terms of noble gas configuration, it is neon 3s2, 3p4. In ions, the electrons are added or removed in the outermost shell only. So electrons are added or removed. How many electrons I can add here to complete the octet? If I say s2 minus, so these electrons are added here. Yes, it is added here. Electrons are added or removed from the outermost shell. Please remember this. Outermost shell. Don't try to remove electrons or don't try to add in the inner shells. Like for example, why I'm telling you this, I know all of you know how to do it, but let's take one example. I'm taking the example of Fe3 plus. So let's write down the configuration of Fe. So what's the electron configuration of Fe? Argon. Yes. Fe is here. Here. So 4s2. What is the outermost shell here? Outermost valence shell. Which one? 4s2, yes. So when you are removing electrons, you have to remove from 4s or 3d? 4s, yes. So when I say Fe3 plus, what's the configuration? So first, you are going to remove electron from here, the outermost shell. Remove from the outermost shell first, and then you can touch your 3d shells. Remove from outermost. So what's the configuration? Yes. Ariba, very good. So it is argon 3d5. Perfect. Correct. Okay. So that's the meaning of the configurations, how to write on the configuration of ions. One last question. Give the configuration of tin 2 plus. Tin 2 plus. Yes, Isabella, what's the confusion? I'm changing my question. I'm not asking tin 2 plus, I'm asking tin 4 plus. Yes, Isabella, ask your question. Are you confused about this one? This is the configuration. Are you okay with the configuration? Then what is the outermost shell? 4s. So you are going to remove. Now what is the charge on this Fe? 3. So how many electrons you have to remove? 3. So remove 2 from here. These 2, remove these 2. This will vanish. And out of 6, 1 is removed, so 5. Okay, now let's do tin 4 plus. First you write on the configuration of tin. Okay, that's the configuration of tin. You see, Afan is giving us. Aditi, I think you have done some error. Tin is here, so krypton is the inner, still some error, Aditi. So the krypton and then it is, okay, sorry. Krypton and then 5s2, 4d10, 5p2. That's the configuration of tin. Now the outermost shell is 5s2 and 5p2. How many electrons I have to remove? 4. So when I remove, then what is left? Aditi, understood? So it is 4d10. So that's how you have to write the configuration of ions. Okay, so moving on. Okay, Ritika is asking a question. If it is tin exists in two oxidation number, Ritika, as tin 2 plus and as tin 4 plus. If I say what is tin 2 plus, children? Ritika, can you give me tin 2 plus? Then in that case, from where you are going to remove electrons? 5s or 5p? Okay, Isabella is asking a good question. So you are going to remove from here. Okay. Why it is going to exist as tin 4 plus? That is okay. So this is stable configuration. You can see that this is fully filled, and exactly half filled are stable. This is fully filled. So tin 4 plus can exist, but very difficult to achieve. Very, very difficult to achieve. There is one more factor. We call it a screening effect. These 4D orbitals, they have a very poor screening effect. They cannot screen the nuclear charge. So these orbitals, especially this 5s orbital, is pulled inside. It's very close to the nucleus. So what happened is difficult to remove electron from 5s. Very difficult, very high ionization energy. We learned this in CBSE chemistry in India, not in AP chemistry. AP chemistry is not asking this question. It's called as inner pair effect. Okay, Isabella? So it cannot exist as 3 plus, because 3 plus means, what is the meaning of 3 plus? 4D, 10, 5s1. Do you think is there any stability here? There is no stability. That is your 3 plus. And what is 2 plus? 5s2. This is 2 plus. This is still okay, because these electrons are very strongly held by the nucleus due to poor screening effect of the 4D orbitals, which is not the part of our learning. So just ignore it. This we are not learning, children. Okay, so any other question here with the electron configuration? Moving on. Now the next important thing is valence electrons are clear to us. I have already given you the valence electrons of every family number 1, alkali metals, their valence electrons are 1 only. Family number 2, these are the general configuration. NS1, NS2, NS2, NP1. For a family, every family, we have a general configuration. This is the configuration of the outermost shell. Like first group, outermost shell is always NS1. Like you can say like this. Okay, here. I can say this is 1s1. This is outer motion. I'm just talking about outer motion. 2s1. What is this? 3s1, 4s1, 5s1, 6s1, 7s1. And before that, you can put these inert gases, noble gas configuration. What about this one? It is ns2, np3, ns2. This one is 2s2, 2p3, 3s2, 3p3, 4s2, 4p3, 5s2, 5p3, 6s2, 6p3, 7s2, 7p3. So every family has a general configuration. Okay, moving on now. Coming on to the next important topic, that is electronegativity and dipoles. What is electronegativity? So before we start with the electronegativity, let's look at this element, hydrogen. Look, you have the periodic table, all of you. Can you tell me how many valence electrons hydrogen has? What's the configuration of hydrogen? 1. So it is 1s1. I'm going to put that electron. This is Lewis dot symbol. Now let's have a look at fluorine. How many valence electrons fluorine has? Look at the periodic table. How many valence electrons? It's in the 7th family, 7. If I make the Lewis dot symbol, then it's like this. Fluorine has a configuration of helium 2s2, 2p5. It needs one more electron to complete the octet. The octet here, 8. After that, which gas is there? Neon. Neon has 8 in the outermost shell, and fluorine wants to be like neon. But fluorine cannot lose. So what they are going to do? Even hydrogen doesn't want to lose. So what are they going to do? They are going to share, right? So hydrogen and fluorine will share these electrons. Once they share the electron, then the electron belongs to both of them. Now both of them are happy. Do you see how many electrons around hydrogen? 2. Now it is 1s2. Shell is full and closed. And this one is 2s2, 2p6, full and closed. So a chemical bond is a pair of electrons. A bond is a pair of electrons. Now this pair of electrons is supposed to be exactly in the center of these two elements. But due to difference in the electronegativity, one element has more tendency to pull this electron pair on itself. Like fluorine. Fluorine is very electronegative. So it will pull the electron pair on itself, creating a delta minus here. Minus means it has slightly extra pair of electrons. These electrons are more closer to fluorine. So because electrons have gone more closer to fluorine due to electronegativity, hydrogen will have delta positive. The bond which is actually should be neutral, it has slight positive and negative charges. This plus and minus charges are due to difference in electronegativity. The element which is more electronegative can pull the electron density, the shared pair of electrons. See the definition here. Shared pair of electrons here in a chemical bond. Electronegativity is always defined in a chemical bond. So there is a minus and the partial delta, delta minus, delta plus. Due to this, there is a dipole. You remember the dipole, children? Dipole has a tip of the arrow like this and the tail like this. Tip always in the direction of negative charge. Tail in the direction of positive charge. This is a vector quantity which has a magnitude and direction. You're understanding this? So electronegativity causes polarity in a bond. If there is a difference in electronegativity, difference I will be writing like this, delta En. If this difference is very large, delta plus, delta minus are large. Big polarity in the bonds. If difference is small, then polarity is less. Based on that, we can discuss the polarity of the molecules, which is very important. And once you know the polarity of the molecule, you can discuss the different types of IMF, intermolecular forces of attraction in the molecules. So let's start. I'm giving you one molecule here, and I'm giving you information. Right now, information is this, that oxygen is more electronegative than carbon. Oxygen is more electronegative than carbon. So what's the partial charge on the oxygen? Minus or plus? Delta minus. Carbon, delta plus. This oxygen, delta minus. Now draw the dipoles. A dipole, carbon and oxygen. You know, dipole has a tip and tail. So tip will be in which direction? Tip is in the direction of oxygen. Yes, and tail is here. Same here. Dipoles are vector quantity. They have magnitude and direction. What do you think? These two magnitudes are equal or different? These two magnitudes are equal, but directions are different, exactly opposite. So what is the sum of these two dipoles? Sum. The sum of these two dipoles, we are going to call it as dipole moment. And this dipole moment is going to tell you whether the molecule is polar or non-polar, right? So the dipole moment is 0. If the dipole moment of one is 0, the molecule is polar or non-polar? This molecule is polar or not? This is non-polar. Yes. But the bonds are polar or non-polar? Chemical bonds. This bond is polar or non-polar? Bonds are polar. So this kind of questions can be there. And I'm going to categorize this molecule as highly symmetrical. Only in symmetrical molecules, dipoles, they cancelled out. If I give you this molecule, then this molecule has a dipole like this. And it has a dipole like this. But these two dipoles, are they equal in magnitude? No. This is sulfur, this is oxygen. So the net dipole moment here is not equal to 0. So what happens? This molecule is polar or non-polar? This is polar. And if this molecule is polar, then what kind of attractive forces this molecule can have? It can have dipole-dipole attractions. The dipole of one molecule is going to attract the dipole of another molecule. It's a polar molecule with dipole-dipole attraction. Okay, so, and I'm going to categorize this reaction as this molecule as not symmetrical. The molecule is not symmetrical. Okay, so moving on, children. So as you have seen that electronegativity is a very important concept. Now we have to understand the trend of electronegativity in the periodic table. I'm giving a very small atom and I'm giving you a big atom. Their orbitals are overlapping and they are sharing electrons. Now, which atom has high tendency to pull electron density? Yes, Kiki, which atom has very high tendency to pull electron density? Small or big? You know, plus minus attract each other. In which case, the plus minus are more closer. This is the plus, plus. Small. Yes, very good, Ritika. Small. So it means when A and B, A is smaller than B, so A will pull the electron density more on itself. So which element is more electronegative? The smaller or bigger? Which element is more electronegative? The smaller one. Okay. Now let's have a look at here. What happens to atomic size down the group? Atomic size down the group increases. So if atomic size down the group increases, what happens to electronegativity? Mhm. Yes, decreases. And this is group, down the group. Can you tell me what happens across the period? Across the period. What happens to atomic size? Atomic size across the period decreases. Electronegativity increases. Remember that. If I follow this, and if I ignore these noble gases and these elements, radioactive elements and the noble gases, can you tell me which elements are most electronegative? Where can I see the most electronegative? Yes, fluorine. This is the one which is most electronegative. In fact, these three elements are most electronegative. Yes, they are the most and this is the least electronegative, this part. Nitrogen, oxygen, fluorine are the most electronegative elements. So whenever these elements make a chemical bond with hydrogen, then the difference in electronegativity is very high. There is a delta minus on the nitrogen, delta plus. This difference is very high, right? And due to this big difference in the electronegativity, if you see this kind of bond in any molecule, this kind of chemical bond in any molecule, then they have hydrogen bonding. Hydrogen bonding. Like for example, if I give you this structure, and this structure, out of these two molecules, which one has hydrogen bonding? A or B? Which one has hydrogen bonding? Hydrogen bonding is IMF, right? Intermolecular forces of attraction. Okay, Isabella, why A? Yeah, not A. Because in A, do you have hydrogen on the oxygen? No, that's why. But B has hydrogen bonding. Hydrogen bonding is an example of dipole-dipole only. It's an example of dipole-dipole. And this one, is it polar or non-polar? What do you think? Is this molecule polar or non-polar? It is polar. The reason is not symmetrical. You can see that. This is delta plus. Oxygen is more electronegative than carbon. You can see. This is delta minus. So there is a dipole here. Carbon and hydrogen bonds are not polar. They are, we cannot say that uh, there is no dipole. There is a dipole, but the difference in electronegativity is very small. Difference in electronegativity is very small. Okay, ready for one question? Rubidium bonded to P. Is there any dipole? Can you give me the direction of dipole? P is here, rubidium is here. Yes. Yes, there is a dipole here. But the difference is very large or very small? The difference is very large, very small, very large. Because this is metal and this is non-metal. So that is the reason whenever a metal is bonded with non-metal, what happens? It's not a bond, it's transfer of electrons, it's ionic bond. They get converted into ions. It's ionic. Because of the, now if somebody ask you that why is it so? So what's the reason? Because the difference in electronegativity is very large difference. So they better lose electrons or gain electrons rather than share. So they don't share. One is losing, other one is gaining. Aditi is asking for ion dipole bond. Yeah, this question many students are asking. And this is a very important latest trend in the AP chemistry of this particular question, the one Aditi is asking. So children understand here. You have already done KSP and all these things with me. Like for example, if I say I'm dissolving NaCl in water, NaCl aqueous. So let's try to understand NaCl aqueous. So there is Na plus, Cl minus, and they are dissolved in water. So water is polar or non-polar? What do you think? It is polar in nature. There is a delta minus here on the oxygen, and there is a delta plus here. So when Na plus and Cl minus are going in the water, Na plus will be surrounded by oxygen of the water because this is plus and this is minus. So it will be surrounded by this one, like this. Can you see that how Na plus is surrounded by oxygens of the water? Water is not breaking apart. Only thing the orientation is that oxygen is pointing in the direction of Na plus. Now what is Na plus? It's an ion. And what is this? This is a dipole. Then we say it's a ion dipole attraction. So whenever you dissolve an ionic compound in water, there is ion dipole attraction. Is it clear? Ion dipole. It's a very important question, children. So all the ions are surrounded by, like Na plus is surrounded by, you can see here, is surrounded by oxygen, like this. And Cl minus will be surrounded by, yeah, which part of the water molecule will surround the Cl minus? Yes, H2O, hydrogen, delta plus. So Cl minus will be surrounded by like this. Hydrogen is in the direction of Cl minus. So if somebody asks you what is this attraction, you are going to say ion dipole attraction. So please write down this. This is important. Okay, so now we are going to discuss different types of polarity of the bond is clear to us. I have already explained you polar and non-polar. Okay, now before we go for the types of IMF, there is one more simple thing. How to count sigma and pi bonds? What is the difference between sigma and pi bonds? So we were talking about elements, they share electrons. Like for example, in this case, how many sigma bonds are there? And how many pi bonds are there? Yes, sigma and pi bonds, sigma and pi. So now I'm going to tell you all things in a very simple manner. When the central element makes its first bond with other element, like this one, this is sigma. This carbon is making this bond. This, any out of these two, anyone, first bond is sigma. So how many sigma bonds are here? Two. And if it is making more than one bond, the second bond is pi. Pi. So how many pi bonds are there? How many pi? Two. Like if I give you HC, triple bond N. Can you tell me how many sigma bonds are here? The very first bond is sigma bond. So what is this? This is sigma. Out of three, this is one is sigma, anyone sigma, and the remaining two are pi. So yes, Ariba is right. So there are two sigma, two pi bonds. If I give you some molecule like this one. So how many sigma, how many pi? So what you do? You make the structure in the elaborated form. And remember, hydrogen never makes a double bond. Hydrogen can make only one bond because it has only one valence electron. So how many sigma, how many pi? All of you, please try to answer this. How many sigma, how many pi? Isabella? One, two, three, four, five. And one pi. If I give you some molecule like this, CH, how many sigma, how many pi? One second. So you make the expanded form. Carbon has how many valence electrons? Periodic table is there next to you. How many valence electrons are there in carbon? 4. So maximum carbon can make 4 bonds. Carbon has 4 valence electrons. It can make 4 bonds. So I'm checking here. I'm making the expanded form. I know hydrogen can make only 1 bond. Carbon can make 4. So it's done. Carbon is done. Then C. You can see that I'm just counting the bonds around carbon. Can you count the sigma and pi bonds now? How many sigma and pi? How many sigma bonds here? There are 10 sigma bonds, okay? Yes, Aditi is also saying 10. And how many pi bonds? 3 pi bonds. Anyone who is not understanding how to count sigma and pi? In multiple bonds, one bond is always sigma, the other bonds are pi bonds. Only one is sigma, others are pi in multiple bonds. If it is a single bond, it's sigma only. Now, what's the difference in sigma and pi bonds? Sigma bonds are formed by real overlapping of the orbitals. Like if this is s orbital and this is another s orbital, so this overlapping is on the axis. Orbitals are overlapping on the axis. So it is called as sigma bond. But if I give you a p orbital which is standing like this, there is another p orbital is also standing like this, their axes are like this, like this. Do you think they can have on the axis overlapping? No, because axes are parallel to each other. They cannot overlap on the axis. So how they are going to overlap? Sideways like this. They will overlap like this, the way it is shown here, like this. So which bond is stronger, sigma or pi? Which one is stronger? Sigma bond is stronger or pi bond is stronger? Remember, pi bond is formed by sideways overlapping. Sigma bond is formed by real overlapping on the axis. Yes. So remember this. This can be a question. Sigma bonds are stronger. Are stronger. Right? Pi bonds are weaker. Okay, so that's the meaning of sigma and pi bonds. Okay, you can see here sideways overlapping. This is the molecule which is drawn here. This is carbon here. Okay, now check. This is pi bond. This pi bond. Can you see the lobes sideways overlapping by the p orbitals on these carbons? They are overlapping like this, sideways. And these are hydrogen on the here. Here you can see sigma bond. This one difficult to break. Which bond is easy to break? Pi bond. So when you're going to learn organic chemistry, you're learning carbonyl chemistry. There, the very first bond we are breaking is pi bond. So we are not breaking any sigma bond. We are breaking pi bond there from this carbonyl carbon, this carbon. So you can learn better if you practice these things. AP chemistry is very important for organic chemistry also. Now I'm coming on the types of IMFs, intermolecular forces of attraction. You can categorize the reaction now, polar and non-polar. You know how to do it? So you will draw the structure, you check the symmetry. If it is symmetrical, atoms are identical, then it's going to be non-polar. But if it is not symmetrical, atoms are different, polarities are different of the bonds or the lone pairs, then the molecule is polar. If the molecule is polar, then you have to identify whether the molecule has hydrogen bonding. You know how to identify that? Or just dipole-dipole. If hydrogen bonding is missing, then you're going to call it as dipole-dipole attraction. For hydrogen bonding, I have given you the hint how to identify that there is hydrogen bonding. If I give you CH4 and NH3, CH4 is very symmetrical tetrahedral. So what kind of molecule is CH4? Polar or non-polar? CH4, non-polar. NH3 is not a tetrahedral. It's not symmetrical. There is a lone pair on this side. So what kind of molecule is this? Polar. If it is polar, then what type of attractive forces are there? It has, do you think it has hydrogen bonding, Ariba? Yes, it has hydrogen bonding. So you know these molecules, they have hydrogen bonding. They have dipole-dipole. Hydrogen bonding is an extreme dipole-dipole due to large difference in electronegativity. And they have London dispersion forces also. These are the weakest, and this is the strongest, right? Dipole-dipole is in between. So in methane, what kind of attractive forces are there in methane? Only LDFs. Now, why are we learning these intermolecular forces of attraction, IMF? Because IMFs are responsible for all the physical changes. Physical changes means like melting, boiling, sublimation. These are physical changes. So IMFs are responsible. We can compare the melting points, boiling points, vaporization, fusion, sublimation, high vapor pressure, low vapor pressure. Afan is saying how to know that where is LDF. Afan, if it's the molecule is non-polar. Here, Lewis dot structure, here we are going to do this only. This is, I'm just giving you a review of these type of attractive forces. The last slide, we are going to do plenty of examples where we are discussing the Lewis dot structure, and then finally we are deciding polar, non-polar. If it is non-polar, then only LDF is there. Only LDF. Afan, non-polar, right? Okay, I'm coming on that question. So first of all, Aslisha is also asking a question. First of all, here, if you see, if the IMFs are stronger, then all these things are high. This can be a question. These are high because you need more energy to break it apart, right? IMFs, you are just breaking the attractive forces. You're not breaking any chemical bond. But the vapor pressure will be low. Please mark it. If two molecules like ammonia and methane, which one has stronger IMF here? Ammonia and methane, which one has stronger IMF? Ammonia. So ammonia is going to have high boiling point, high melting point, high delta H of vaporization, fusion, sublimation. But ammonia is going to have low vapor pressure than methane because ammonia needs more energy to get converted into vapors. Vapor pressure is due to vapors. So the tendency of ammonia to vaporize is less. Children, are you getting this? You're understanding this? Okay, I think Aditi, are you answering? Yeah, good, Aditi. That's the right answer. I'm coming on that. Aditi has already answered your question. So Aslisha asked me that if butane have stronger IMF than propane. So this language will not be there in the examination because butane is an organic compound and the nomenclature we are not learning in AP chemistry. So butane is this molecule. It has 4 carbons. This is butane. Its molecular formula is C4H10. Propane is 3 carbon, CH3, CH2. You remember I told you that the difference in electronegativity of carbon and hydrogen is very low. Okay, now which one has bigger size and high molar mass? This one. This is big size, more atoms, big size, and high molar mass. And LDF depends on that. More big is the size, more high is the molar mass is high, big size, then LDFs are stronger because LDF depends on the polarizability. Okay, but that's not correct, Aslisha. AP chemistry people are not going to ask this. In your teacher, like she gave you any information about these organic compounds before placing it in the examination? Oh, but organic compounds are out of AP chemistry. I think it was just before 2015. So don't worry, these names will not. Formula can be there. They can give you the formula, but not the names. Okay, they can give you these formulas. They will give you the formulas, but not the names because we are not doing nomenclature. Earlier we used to do. So maybe your teacher is not aware that nomenclature is not the part of learning. Yeah, Lewis structure you can draw. Yes. Simple molecules, not the big one. Okay. We are Lewis structures of like CH4. That can be the part of your learning. C2H6 can be the part of learning. But very big molecules like this compound is also organic compound. This one. These are simple molecules. So their Lewis structures can be. Okay, but nomenclature, butane, propane, they will not give you these names. So dispersion forces or London dispersion forces, they are also called as induced dipole. They depend on two factors, molar mass and surface area, big size, small size. Why? Because if a molecule is big, understand this. If a molecule is big, like iodine is very big molecule, is in the fifth period. Its outermost shell is 5s5p, very big outermost shell. Orbitals are big. So the electrons of the outermost shell are away from the nucleus. So the force of attraction on these electrons is very less. So what happens when there is some other molecule? Now let's say this is another iodine molecule. So the nucleus of one iodine molecule can attract the electron cloud of the other iodine molecule like this. And this electron cloud will move like this. And when this happens, there is a slight negative and positive charge is created like this. This is a very weak dipole, temporary dipole. It comes, goes off like this, temporary. Okay, it's not a permanent dipole. So iodine I2, is this I2 polar or non-polar, children? This one is polar or non-polar? It is non-polar. So in non-polar molecules, we are not expecting any charge separation. But due to this polarizability, that iodine molecule should be perfectly spherical here like this, perfectly sphere, the complete molecule. But actually what happened? That it gets polarized. So there is induced dipole, or temporary dipole. You can see the dipole here. This is very weak. So attractive forces are weak and they fall in the category of London dispersion forces. So can you answer this question here? This one. All these molecules are non-polar. I'm giving you information. It's written here. So why this melting point is increasing? Explain. So once it is said that they are non-polar, then what kind of attractive forces they have? LDFs. Now, what is happening to their molar mass and size? It's increasing. This one has the highest molar mass and the size. Dhruv, you're not answering. And this one is, that's why it has the highest melting point. So this can be a question. What about this one? Answer this. What are these molecules? Polar or non-polar? F2, Cl2, Br2, non-polar. So what is happening to the melting point? So once you decide non-polar, then think about type of attractive forces. Attractive forces are LDF. So what is happening? Attractive forces are increasing. Why? So there is increase in molar mass. One more factor, Aditi. State of matter is changing because attractive forces are increasing. Question is why the attractive forces are increasing? That's the question. Can you see this is gas, liquid, solid. So it means attractive forces are increasing. Why the attractive forces are increasing, Isabella? Ritika? Because attractive forces are LDFs, London dispersion forces, and they depend on molar mass and yes, polarizable, and second factor, size. So please memorize these two factors. Okay, so if somebody is asking like this, then first decide polar, non-polar. If it is non-polar, then think about LDF. LDFs, then just bring these 2 points in your mind. Okay, molar mass and size. Then make your answer. More high molar mass, more is the polarizability. Polarizability means that induced dipole. Okay, now I'm coming on the one more example from organic chemistry that can be in the exam. Butane. You remember, Aslesha was saying butane. Butane can exist. This example I discussed in my notes also. CH3, CH2, CH2, CH3. This is pentane. Okay, I made pentane, no problem. Pentane, you can see 5 carbons. This is a straight chain compound. straight chain. All carbons are in the chain. If I draw it like this, 1, 2, 3, 4, these are carbons. It's like this. But if I make, and its molecular formula is C5H12. Now making is isomer. Isomer. Iso means dhruv. Iso means same. Isotopes, isobars, isomers. Mer means molecules. Same molecular formula. Again C5H12. But the structure is different. This time it is like this. CH3, CH, CH2, CH3. Yes, Sanjana. If I draw the line picture, this is called as line notation, then it will be like this. Can you tell me which molecule you're expecting to have higher? These molecules are polar or non-polar? Let's decide first. All hydrocarbons are non-polar. So write it down somewhere, because the difference in electronegativity of carbon hydrogen is very less. So all hydrocarbons are non-polar, right? So now can you tell me which one has more bigger surface area? Mhm. Which one has more surface area, more spread out shape? This one is more spread out. And these are non-polar molecules. So please write down somewhere, it's written in my notes also. All hydrocarbons are non-polar. So they are non-polar. But this one is more spread out. More spread out, more surface area means more LDF. There is more LDF. More LDF means higher boiling point. So pentene isomer, which is a straight chain, we call it as normal pentene. And we call this one as isopentene. Normal pentene has higher boiling point than isopentene. So this question can be there in the exam. But don't worry, they will give you the structures to make you understand. You need not to memorize these names. Okay, so hydrogen bonding, I have already explained you. And dipole, if there is a polarity of the bonds, then either it is hydrogen bond or normal dipole. So can you tell me what kind of attractive force is here? Identify IMF. So we are going to identify IMF in all these molecules. Yes, HCl. What type of attractive force? Yes, Sanjana, very good. Dipole, and LDFs. What kind of attractive force? They are saying it's non-polar because it's symmetrical tetrahedral. Only LDFs. What kind of attractive force? It's a symmetrical trigonal planar. Only LDFs. Very good. What kind of attractive force? Name the attractive force. Yes, LDFs and which one is stronger? Dipole. Check this one. What kind of attractive force? This molecule. Yes, this one has hydrogen bonding and dipole. Good. Okay. Do you think this molecule, what kind of attractive force is there in this molecule? You can see the molecule, organic molecule. Identify the attractive force here. Do we have hydrogen bonding in this molecule? No, there is no hydrogen bonding. Why? Because there is no hydrogen on the oxygen. That's why. Okay. And what kind of attractive forces are here? I gave you one statement. Hydrocarbons are non-polar. So only LDF. So you can compare the melting boiling points, right? You can see the difference in the boiling point. This is minus 0.5 degrees Celsius. And this is 56.2 degrees Celsius. So that's about the IMFs, different types of IMFs. Now, formal charges. This is very important, children. So pay attention and keep answering my questions because we are going to do plenty of questions here. See this box I have made. So we'll do minimum, I want to do 15, 20 different examples to make you expert in doing these type of questions. So the very first important point is formal charges. If you understand that, you will not do any error in the Lewis dot structure. Okay, what is formal charge? Formal charge is valence electrons. Simple definition. It is the valence electrons. You know how to see the valence electrons? Minus electrons used in Lewis dot structure. Lewis dot structure. That's the meaning of formal charge. Now let's see. H, O, H. Look at this oxygen. How many valence electrons are there on the oxygen? Remember, sixth family, sixth group. How many valence electrons on the oxygen? 6. So oxygen is giving its 6 valence electrons for bonding. Now out of 6, how many are there as lone pairs? 4. And for every bond, oxygen is giving 1. So out of 6, how many are used? How many are used? 6. So what's the formal charge? 0. So elements are using their electrons as lone pairs or as bond pairs. They are using in this two different manner. So as lone pairs, they go as whatever number of lone pairs are there, you multiply it by 2, 2 times lone pairs. As in the bond pair, they are giving only 1. So if there are 2 bonds, so it means there are only 2 electrons. So number of bonds. So this is the equation which generally I'm using. That formal charge is valence electrons. Just count the number of bonds because every bond is 1 electron. And then 2 times lone pair. So you can use this equation, which I have explained you in detail earlier also. Ready now? Okay. Now see here. I'm going to tell you the meaning of expanded octet also. So let's work with these elements. Boron has how many valence electrons? Boron has how many valence electrons? 3. So it can make maximum 3 bonds. And you can see boron like this in the molecule, or you can see boron like this in the molecule. But if I say that boron is present like this, what's the formal charge on boron? Can you count the formal charge on boron? You can use this equation or this equation, whatever you are comfortable. What's the formal charge on boron? In this case, it is 3 minus 3, 0. In this case also 3 minus 3, 0. How much is here? Minus 2. Yes, it is -2. Yes, very good. Perfect answer. Okay, now I'm giving you another example. Carbon. How many valence electrons carbon has? 4. If I show you carbon like this, what's the formal charge on carbon? Yes, 0. 4 minus 4. If I show you carbon like this, what's the formal charge on carbon? Mhm. Charge. Charge means, yes, Ritika, you're right. Charge, you have to tell me plus minus, okay? And if I give you something like this, then what's the formal charge on carbon? Isabella, you're not answering. I hope you're understanding everything. Okay. What's the formal charge here? Yes, -1. Okay. Do you think carbon can make bonds, 5 bonds? Do you think carbon can make 5 bonds? And what is the reason? No. Elements of the second period, their outermost shell is second period elements. I'm talking about second period elements, children. Second period elements, their outermost shell is 2s2p. Maximum, how many electrons you can have in 2s2p? Maximum. 2s2, 2p6, maximum 8. You cannot have more than 8. Do you have 2d? Empty 2d there? Do we have? No. There is no 2d. D starts from 3. 3d is there, 4d is there, but there is no 2d, right? You know that electron configuration when we were writing, then this is 3d, 4d, 5d, 6d, but there is no 2d. So now this is a very popular question. Why second period elements cannot have expanded octet, cannot have more than 8? Because they don't have vacant 2d orbitals. They don't have any orbitals. Shell is closed. After 2p, what happens? Shell is closed. There is no more empty d orbitals available. So no expanded octet. So when I make 5 bonds around carbon, is it feasible? How many electrons are there? Count the electrons. Every bond is 2 electrons. Every bond is 2. So how many are there right now on carbon? Yes, Safan. How many electrons are there on carbon? Count it. They are visible, these white electrons. 10. Do you think carbon can have 10 electrons? No. So remember, carbon will never make more than 4 bonds. Same with nitrogen. Nitrogen will also never make more than 4 bonds. But nitrogen is going to make 3 bonds and 1 lone pair because it has 5 valence electrons. That's the combination which is going to get fitted over there. 3 bonds with 1 lone pair. So it can be like this. It can be like this. It can also be like this. This is how nitrogen can be seen. In all these cases, nitrogen has 0 formal charge. Check it. But you will see nitrogen like this also. Can you tell me what's the formal charge on this nitrogen? Yes, please. All of you, work out the formal charge on this nitrogen when it has 4 bonds around it. What's the formal charge? +1. Yes. You're using which equation? So children, you can use this one or you can use this one. This is the equation which teachers are also giving in the school. So whatever way you are comfortable. Use the equation, just see how many valence electrons nitrogen has, 5. How many it has used in the bonding? 4 bonds, 4 electrons. Any lone pair? 0. So +1, like this. Okay, this is about the second period elements. Like fluorine. Fluorine can also, it cannot have expanded octet, and it is already with 7 electrons, 7 electrons. So how many maximum bond fluorine can make? How many maximum? 1 only. But as I start talking about third period elements, then their orbitals outermost shell is 3s, 3p with 3d. You're going to fill electrons in 3s and 3p, but 3d is lying there. It is there because period number 3, shell 3 is introduced. 3d is vacant, totally vacant. So it can take extra electrons. Like for example, sulfur. How many valence electrons sulfur has? Mhm. 6. You know maximum how many bonds sulfur can make? How many bonds sulfur can make maximum? 6 bonds. It can have an expanded octet. So children, I'm showing you sulfur can make maximum 6 bonds. How? This is 3s filled like this, one up, one down. This is 3p, one up, one down, like this. This is how we have to fill electrons, showing the spins up and down. Okay, now this is empty 3d. If these electrons, they don't excite, how many bonds sulfur can make? Check here. How many are unpaired? 2 electrons are unpaired. So it can make only 2 bonds. So if I take it like this, then sulfur is like this with 2 bonds, 2 lone pairs. Check the formal charge, 0. Oxygen is also like this. Oxygen is also can make 2 bonds with 2 lone pairs. It can make multiple bond like this. Oxygen, sulfur, same family. Sulfur also like this. But if I make one electron jump from here to here, now how many unpaired electrons? Yeah, please answer here. How many unpaired? So how many bonds sulfur can make when it has 4 unpaired? Nivriti, are you answering the number of bonds in this particular structure here when it is like this? How many unpaired, Nivriti? 1, 2, 3, 4. 4 unpaired, so it can make 4 bonds. It can invite 4 electrons for bonding. Okay, so that's the thing like this. Check the formal charge. Do you think oxygen can have something like this? Do you think I can make oxygen like this? No. Why not? That's the question. Why not? Because it doesn't have empty d orbitals. Yes, very good. Perfect. So this cannot happen. Can I make one more electron jump, children? Yes, one more electron can jump. And now, how many bonds sulfur can make? 6. What's the formal charge in all these cases? 0, 0, 0, 0. We are understanding this, children? This is very important. So, which elements can show us expanded octet? Second period elements, third period elements, and onwards. All these, they can show you expanded octet. Like chlorine has 7 valence electrons. So what do you think? Chlorine can make maximum how many bonds? Maximum. How many bonds chlorine can make? 7 bonds. There is a structure of chlorine. You're aware of perchlorate ion? This is perchlorate. Check how many bonds chlorine has. Maximum 7. It can make 1 bond. It can make 3 bonds and with 2 lone pairs. It can make 5 bonds with 1 lone pair. It can make all 7 bonds. Okay, so we are going to become expert in this while we are making Lewis-Dot structure. So I'm taking you on the next slide, which is the most important one. That's the target, children. How to draw the Lewis-Dot structure. So I'm giving you one PDF here. You can take a print out of it. Keep practicing from this PDF. So please download it. And right now also we are going to use it. These are the rules to make the Lewis-Dot structure. We are starting with an example. The example which I'm giving you is SO4 2 minus. That's the example. This is the example. Follow the rules. Rule number 1 says select the central atom in SO4 2 minus, select the central atom which is less electronegative, least electronegative. Oxygen is here, sulfur is here. So which one is the central element? Sulfur. Put it in the center. Rule number 2, make the skeleton with other atoms. The other atom is oxygen. Right? So put oxygen. How many maximum bonds sulfur can make? How many? How many maximum bonds sulfur can make? 6. And how many maximum bonds oxygen can make? Oxygen can make only? No, oxygen. Oxygen. No, Isabella, oxygen. 1s2, 2s2, 2p4. How many more electrons are needed to complete the octet? So it can make only 2 bonds. Like fluorine. Fluorine can make only 1 more bond. Oxygen can make only 2 more bonds. Nitrogen can make only 3. If you make more than 3, it gets a formal charge. Right? Carbon can make 4. Okay. They cannot have expanded octets. So whatever number of unpaired electrons they have, they can make only that much number of bonds, right? To complete the octet. So now the third rule says count the total valence electrons. And if there is a negative charge, add it. If there is a positive charge, subtract it. How many valence electrons sulfur has? How many valence electrons sulfur has? 6. And 4 times how many oxygen has? 6. And plus 2, this 2, 2 minus. 2 minus means extra 2 electrons. So how much total? 32, very good. Now see here, I've given you hints. I said sulfur can make 6 bonds maximum. Oxygen can make only 2 bonds. So I'm making double bond on this oxygen. And I'm going to complete the octet by 2 lone pairs. Can you see? It is with 8, 8. This one also with 8. Can I make more double bonds, children? Dhruv, can I make more double bonds? No, because sulfur is done. Now, don't make more double bonds. Now, how many electron pairs I have to place here? 3. To complete the octet, now 6 plus 2, 8. 3 here. Now start placing formal charges and check how many you have placed. How many you have placed? 8, 8, 8, 8, all 32. So all electrons are used up. Nothing left. You are done. But you have to show the formal charge. So check the formal charge. What's the formal charge on this oxygen? On this one, children? Yes, -1. On this one? -1. And on this one? On this one? Yes, Kiki, very good. On this one? And sulfur? Sulfur? 0. Okay, fine. Now we are answering these questions, children. We have made the Lewis dot structure of sulfate. Groups. Groups are the lone pairs plus atoms. So tell me, how many lone pairs and how many atoms are there around sulfur? Lone pairs and atoms on the central element. 4. If there are 4 groups, what's the hybridization? Remember, hybridizations are sp, sp2, sp3, sp3d, and sp3d2. sp when you're mixing 2 orbitals. sp2 when you're mixing 3. sp3, 4. sp3d, 5. sp3d2, 6. It depends on the requirement. How many are needed here? 4 orbitals. So I'll mix 4 orbitals, means sp3. So hybridization is sp3. And the bond angle from here, from sp3, we are going to say sp3 are tetrahedral. Tetrahedral. Tetrahedral means you're going to make the structure like this. I have already made it tetrahedral, so I'm just going to make it again. Sulfur in the center. There is a double bond O. This is tetrahedral shape. This one. Angle is, you have to memorize the angle, children. All these things are given here in this PDF, the one which I have shared. So check the PDF. Start looking into it. If you don't know something is missing from your knowledge, look into it and answer here. And you will see it will help you in memorizing. So bond angle is 109.5 degree. How many atoms are there around sulfur? Atoms, not the lone pairs. How many atoms? 4. How many lone pairs? 0. So what is the electron pair arrangement? For the 4, for the sp3, 4, electron pair arrangement is tetrahedral. But what is the molecular arrangement? Same tetrahedral, because there is no lone pair on the central atom. Same tetrahedral. Is it symmetrical or distorted? Yes, check this molecule. What do you think? Symmetrical or distorted? You're going to say it is ionic. It's an ion. It has negative charge. Ionic. What's the polarity of the molecule? Is it polar or non-polar? Again, you are going to say ion, very polar. What type of IMF this molecule has? Yes, children, what type of IMF? Okay, I'm making the molecule here. Identify the IMF. Ion-ion attraction, isn't it? It's ionic. It's ion-ion attraction. Type of IMF. Ion-ion attraction. Number of pi bonds. Count the number of pi bonds. Pi bonds. And count the number of sigma bonds. Sigma bonds? 4. So this is the first example, okay? So children, answer my question. If there are groups, what is the meaning of groups? Groups means atoms plus lone pairs. No, Aditi, groups are the domains. Atoms plus lone pairs are the domains. That is called as EPA, electron pair arrangement, or they call it as electron domain geometry also. You have to count lone pairs also. Atoms and lone pairs. Any other question from here, children? Please keep asking your question, because I know that all of you are doing review, examinations are going in the school. So if something is not clear, start asking. Aslisha, you are back or you are not back yet? Aslisha, are you there? Okay, good. Ready? Groups means atoms and lone pairs, which is going to decide the EPA. EPA or EDG, electron domain geometry. You can call it as electron pair arrangement or electron domain geometry. That will be decided by the groups. If groups are 2, what's the hybridization? All of you, please try to answer. If groups are 2, hybridization is? If groups are 2, yes, Ritika, very good. If groups are 3, hybridization is? 3 groups, sp2. If groups are 4, hybridization is? sp3. If groups are 5, hybridization is? No, Dhruv, no, there is no, Aditi, no. Do we have 4 p orbitals? We don't have 4 p orbitals. You know, p orbitals are only 3. px, py, pz. sp3d. If groups are 6, then it is sp3d2. Ready for a question now? Now we are going to do plenty of questions. Whatever time is left, that is only questions and questions. Okay. Here comes the question. Just moving it slightly up so that you can see the periodic table. Okay. The molecule is SO3. Draw the Lewis dot structure. Follow the rules. Central element. Central element. S. Skeleton. Make 3 bonds with 3 oxygen. Count the total valence electrons. Look at the periodic table. Sulfur and oxygen. The total valence electrons are? Sanjana is saying 24. She's right. How many maximum bonds sulfur can make and how many maximum bonds oxygen can make? Sulfur first. How many maximum? And oxygen? Oxygen. Now focus on oxygen. Focus on oxygen because you have to complete the octet of the more electronegative. The rule is saying that. Complete the octet of more electronegative element with minimum formal charge is written here. So put a double bond and 2 lone pairs. I think oxygen is happy like this. Check the formal charge for happiness. Is the formal charge on this oxygen 0? Is the formal charge 0 here? Mm-hmm. Isabella, formal charge 0? Kiki, formal charge is? Kiki, you are there? 0. Okay, good. Perfect. Now, what should I do with the other oxygens? What do you think? Now you have all the picture in your mind. Sulfur can make 6 bonds, oxygen can make 2. So what can I do with this oxygen? Can I do the same thing? Same thing, right? Can I do the same thing here? Yes, Afan. So tell me the groups. This is the Lewis dot structure. We have used all 24 electrons, 8 here, 8 here, and 8 here. All 24 are used up. Count the groups. Now answer my questions. I want all of you to please answer. Otherwise, you will not learn the way I want you to learn for this, because these are questions. These are your multiple choice questions, free response questions. So to answer these questions, all these questions, first we have to make the Lewis dot structure. Every time, draw the Lewis dot structure and then start answering the questions. Without Lewis dot structure, you cannot answer. So how many groups are there? Yes. How many groups on sulfur? Groups means atoms plus lone pairs. Yes, please. Only Aditi has answered. Ritika is saying 3. Aditi is saying 3. What about rest of you? Ariba? Yes, it is 3. Good. What's the hybridization? Try to be first. Yes, very good. sp2. Now I have given you the list. Check the list. What is the bond angle for the sp2? Yes, 120 degree. These are fixed things, fixed. If groups are 3, it is sp2, angle is this. And how many atoms are there on sulfur? 3. How many lone pairs are there on sulfur? These are on the sulfur, on the central element. On the sulfur. 0. What is the electron pair arrangement? That you are going to decide from here. It is trigonal planar. Very good. What's the shape? Any lone pair on the sulfur? No. So any distortion? No. So shape is also trigonal planar. You are getting it? Same. Both the things are same. Is this molecule symmetrical or distorted? Yes. What do you think? It is symmetrical. The molecule is symmetrical. If the molecule is symmetrical, what about the dipole moment? Net dipole moment is? Yes. For a symmetrical molecule, net dipole moment is 0. So the molecule is polar or non-polar? Molecule is polar or non-polar? It is non-polar. So what type of IMF the molecule has? What type of IMF? Only LDFs. Yes, only LDFs. How many pi bonds? How many pi bonds? 3. How many sigma bonds? 3. You can answer all these multiple choice questions provided you draw the right Lewis dot structure. If you do error here, then all these will go wrong. Ready for another example? We are doing another example now, children. I'm going to erase this. SeO2. Bring down this periodic table here. Yeah, now it's okay. SeO2. Center element. Yeah, start answering. Central element, least electronegative element, Sc. Do you think Sc can have expanded octet? It's here. It's here, Sc. Sc can have expanded, okay, very good. Sc can have expanded octet. Yes, good. Make the skeleton with 2 oxygen. Count the total valence electrons. Third rule, total valence electrons. Yes, who is doing it? 18. Yes, okay. Now complete the octet of the oxygen. How many bonds oxygen would like to make? 2. So make a double bond. You have to complete the octet of the most electronegative atom with minimum formal charge. So put 2 lone pairs. Octet is done. What's the formal charge on this oxygen here? 0. Put a double bond. What's the formal charge on this oxygen here? 0. How many are used? How many are left? You know that selenium has 6 valence electrons, right? It has used only 4. 4 bonds means it has used only 4. So how many are left out of 6? 2 are left. So there is a lone pair. There is a lone pair on selenium. You can do like this also. 8, 8, 16. 18 minus 16 is 2. These 2 electrons will come on the central element as lone pair. Right? Okay, start answering. How many groups on selenium? Groups. 3. What's the hybridization? sp2. What's the bond angle we are expecting? 120 degree. But do you think this is exactly 120 degree? Okay, now here comes one more concept. When we decide the bond angles, if all the 3 are not bonds, like here there are 3 groups, but out of 3, only 2 are atoms, right? So this lone pair can cause more repulsion. I'm writing here, children. Lone pair repulsion is more than lone pair bond pair repulsion. I'm talking about repulsion. Repulsion means they tend to go away from each other. They tend to go away. Repulsion, go away. Lone pair, bond pair. And then bond pair repulsion is minimum. So maximum repulsion is here. So they try to occupy more space. They spread out more. Then lone pair, bond pair. Now this lone pair will spread out more and is going to push the bond pair closer. So angle will be slightly lesser. Slightly lesser than 120. Is it okay? Okay, how many number of atoms are there, children? 2. How many lone pairs? 1. What's the electron pair arrangement or electron domain geometry? What is it? With the 3. That you are going to decide from here. It must be written here. Trigonal, planar. But out of 3, 1 bond is missing. Can you see? 1 bond is trigonal planar means like this. Like this. This is trigonal planar. It should be like this, right? But this bond is missing. There is no such bond. Where are these lone pairs? They are in the orbitals. In the orbitals of the selenium, like this. What is appearing to you? If out of 3, there are 2 atoms and 1 lone pair, then it should be bent. Now you can see your molecular geometry and the electron pair geometry is not identical, it's different. They are different. There is no symmetry because this lone pair is going to exert a bigger dipole than these two. Dipoles are not same. So the molecule is symmetrical or distorted? Is the molecule distorted or symmetrical? We're going to call it as distorted. Who is making it distorted? The lone pair on the central atom. So is this molecule polar or non-polar, children? The bent? Is it polar or non-polar? It's polar. If it is polar, what kind of IMF this molecule has? What kind of IMF? Yes, dipole and LDF. So first we are going to list the stronger one, dipole and LDF. If they say list all the IMFs, then mention LDF, otherwise dipole. How many pi bonds? And how many sigma bonds? How many pi bonds, Nivriti? There are 2 pi bonds and 2 sigma bonds. Are you understanding these questions now? Ready for one more example? Okay. Ready, children? Follow the sequence of thinking. Okay, it's very important. POCl3. That's the example. Now, first step, draw the Lewis dot structure. Center element, make the skeleton. Skeleton means make single bonds with other elements. Like this. Chlorine here, and another chlorine and oxygen. Am I right? This is the skeleton. How many, once you have made the skeleton, search these elements in the periodic table. Check your central element can have expanded octet, yes or no? The central element. P, Aditi, central element, this P. Yes or no? P, phosphorus, third period element. Outermost shell is 3s, 3p. It can have empty 3d. So why are you saying no? The phosphorus element can have expanded octet. Isabella, yes or no? Yes, children. Is it difficult to understand that P can have expanded octet? Aditi, is it clear? How many maximum bonds P can make? Check the group number. Group number is 5. So how many maximum? Okay, in what? Isabella, ask your question. What is the question? Afan, you're understanding this? Okay. The question Isabella is saying, why is going to be expanded octet? Because if you see the total number of valence electrons here, P has 5, oxygen has 6, 3 times 7. How much is this, Isabella? 21 plus 5, 21 plus 5, or in total 32, right? Now you have to put these 32 electrons around this P. In this complete structure, I have to put 32 electrons. And I have to make everyone happy. Oxygen should be happy, chlorine should be happy. And when I'm trying to do that, I'll focus on P. P is in the third period, is third period element, right? Third period. Third period means 3s, 3p with empty 3d. So P has 5 valence electrons, 2 and 3 here. One electron can jump from here, can go here. Now you can see it has total 5 unpaired electrons, so it can make 5 maximum bonds. Because when it makes 5 bonds, then you will see oxygen, chlorine, they all are with 8 and they all have formal charge 0. If you don't make that, you will not get the right answer. Isabella, you're understanding this? Okay, it will be more clear as we'll keep making it. So how many bonds oxygen would like to make? Maximum. That already you know. How many? 2. So it means this oxygen is going to make a double bond. That's the only option it has. And then 2 lone pairs. Is the octet done? Is the octet done? Yes. Oxygen is very happy. 0 formal charge. Oxygen is with 0 formal charge, right? You can check it. You can count it. I gave you the equation how to calculate formal charge. How many maximum bond chlorine can make? How many valence electron chlorine can have? 7. It has 7 valence electrons, so it can make here, it can make only 1 bond. Why? Because it is not the central element. Only central elements, they tend to go for expanded octet. Central element. The elements which are not in the center, they will not expand their octet. So chlorine has 7 valence electrons. It needs only 1 more. So it's going to make only 1 bond. Right? How many electrons I have used? Check how many electrons are used. 8 here, 8 here, 8 here, 8 here. All 32 are used up. But when I'm doing this, trying to satisfy the octet of chlorine and oxygen, which are more electronegative, and according to the rule here, I have to take care of these more electronegative atom first. So when I was taking care of this, how many bonds I have made around P? Check. How many? 1, 2, 3, 4, 5. But I can make 5 bonds only when it can have expanded octet. And when I looked at the periodic table, I can see P can have expanded octet due to the presence of empty d orbitals. Is it clear why P has expanded octet here, Isabella? If you don't make it, your structure will be wrong, because then you cannot satisfy your oxygen at all. Okay, now start answering these questions. How many groups on P? Groups on P. What's the hybridization? What's the bond angle? Number of atoms on P. Lone pairs on P. Electron pair arrangement or electron domain geometry, which is decided by from here. Tetrahedral. Okay. Molecular geometry of the shape. Do you have any lone pair of P? No. So what's the molecular geometry? Tetrahedral, which I'm writing as TD. Is it symmetrical or distorted? Is this molecule Nivitri symmetrical or distorted? Yes, Sanjana, good. It's distorted. Why? Because atoms are not identical. You can say not symmetrical, right? The molecule is not symmetrical. Yes. Why? Because all the atoms are not identical. Is it polar or non-polar? The molecule is polar. What type of IMF is there? What type of IMF? Yes, dipole, dipole. Dipole, dipole. Number of pi bonds and number of sigma bonds. Who is saying 3? What is 3? Isabella, 3 is what? Okay. Number of pi bond is 1 and number of sigma bonds are 4. One last example and we'll continue on Sunday also. You have a morning class. Group 3 regular Saturday evening class is there, and group 2 and group 3 both the groups are here today. And so Sunday morning class is there for all of you. But group 3, please understand your regular normal tutoring class will be there. One last example before we end the class. Ready, Dhruv? You are going to answer all of them. And it is PO3 3 minus. Central element, skeleton, total valence electrons, total valence electrons. 26. Okay, I'm taking 26. You added this 3 minus, Aditi. 5 for P, 3 times 6 oxygen, and this 3 minus means extra 3. So I think she's right, 26. Good. Complete the octet of oxygen first. Check for P. P can have expanded octet. How many maximum bonds P can make? 5. Don't try to make more than 5. Okay. And oxygen wants to make 2. So make a double bond here. And can I make one more double bond? Can I make another double bond, Dhruv? Can I make one more here? No. So this I have to place 3 lone pairs. How many I have used? How many I have used? 8 here, 8 here, and 8 here. All are used. Okay. Put the formal charges. No, not all of them are not used. Can you see? 8 here, 8 here, and 8 here. I've used extra. No, one lone pair is left. One lone pair is left. And where should I place it? Yes, 2 electrons are left. And these 2 electrons, they can be placed on the P. Right? Actually, P cannot take more because P is already with 5 bonds. P cannot take more. So remove this lone pair and remove the double bond. Put 1 here, negative. This is the structure. Now check the formal charge. This oxygen is minus, this oxygen is minus. What's the formal charge on P? Do this calculation, children. And we'll do this example again because there is some confusion. So we'll do it again in the next class. Check the formal charge on P. Kiki, what's the formal charge? Formal charge on P. It is valence electrons 5 minus number of bonds 4, and then there is a lone pair. So the formal charge on P is also -1. That's the correct Lewis dot structure. You can see there is 3 minus here. This oxygen is -1, this oxygen is -1, this P is -1, this is 3 minus. Is satisfied. Okay, can we do it this one fast? How many groups on P? Groups on P. No, Aditi, no, Ariba, no. Afan is right, 4. Groups on P. Lone pairs plus atoms. Lone pairs plus atom. There is 1 lone pair and 3 atoms. And if it is 4, what's the hybridization? What's the bond angle? It will be slightly lesser, slightly less. Agreed? Slightly less. Why? Because there is a lone pair. Lone pair will distort the shape. So angle will be slightly less. How many atoms? How many atoms on P? 3. How many lone pairs on P? 1. What's the electron pair arrangement? Okay, Kiki, you can go. What's the electron pair arrangement? It's tetrahedral. What's the molecular shape? Molecular shape is not tetrahedral because when I make the tetrahedral, it will appear to you like this. Like this. It's trigonal bipyramidal. Yes. Who is this? Dhruv. Very good. So please practice this table. Trigonal bipyramidal. Is it symmetrical or not symmetrical or distorted? It is distorted by lone pair. Distorted. Is it polar or non-polar? It's polar. What type of IMF? Type of IMF. Dipole, yes, very good. But you are not going to say dipole. Should I say dipole, children, or should I say ion? Ion. It's going to have ionic attractions. Okay, I'm going to check it, Aditi. Number of pi bonds. How many pi bonds? 2. How many sigma bonds? 3. So Aditi is pointing out some error in the PDF. That's the EPA, Aditi. Aditi, there is no error. Tetrahedral, they all are tetrahedral in EPA. But 3 and 1 is trigonal pyramidal. See here. So children, I hope that you have understood something because this is very important. I'll continue with this in the next class also. PDF is already with you. Take a printout, and in the next class, we'll do minimum 10 more examples. And in the starting of the class only. So please come prepared and try to answer and ask questions and be very clear about it. So we'll do difficult examples. Minimum 10 examples we are going to discuss here. So see you in the next class tomorrow.